for its minimal necessary data, the case for analyzing training data requirements of recommender algorithms. This paper was given at the Workshop on Responsible Recommender Systems at ACM RecSys 2017. This talk doesn't contain anything you probably don't know. Its point is that recommender system algorithms should use no more data than they strictly need, and by adhering to this principle, which is a principle of good engineering, we also have benefits for user privacy. So the roadmap of this paper, first of all, we look at the question of, is all this data really necessary for making good recommendations? Here we look at the results of some classic RecSys experiments. Then we move to the question of, well, why is privacy important? At the RecSys banquet, I was asked, why do you work on privacy? So I realized that this is not obvious, so I'm going to state it here. And finally, we talk about training data requirements analysis, which is actually the point of this paper is to encourage people to do this in their recommender system work. Okay, so let's get started. Time moves forward, and as recommender system research moves forward, we realize more and more that in real world RecSys data is temporal. And so when you're doing evaluation, you get a picture that looks like this. Here's your test data, and your training data stretches back in time like this. So this is a batch setup, and each of these are segments of the temporal segments of the data set. So it means if you do cross-validation, then we have a picture that looks like this. Here's 4 folds, and the test set moves back in time, and each time the training data set also moves back, so that the training data is chronologically ordered before the test data. So this is the setup that we use in the experiments that we do here. In particular, we use time truncation of the data. We start with our full historical data set like this, and then we truncate and use less and less of the data and see what happens. Well, nothing really surprising happens. Here are our findings on the MovieLens 10 million data set. So this is RMSE. The x-axis here represents segments of the data set, approximately 10% of the data set each time. And we see as we add more and more training data to the model, at a certain point here, the added value of each additional segment becomes vanishingly smaller, non-existent. Okay, so we have bias matrix factorization, the red line, and we see that factorization machines are doing a bit better, but the trend is still the same. So in this talk, we don't discuss the algorithms in detail. I'm not even giving the specifications of the data set, but rather we refer you to the paper in the FATRec 27 proceedings for that. So the point here is that we have a saturation point here after approximately 30% of the training data has been used. So we did this on other classic recommender system data sets, and each time we see that we see a point after which the amount of improvement that's being gained by additional data becomes smaller. And I call your attention also to the y-axis here. So in some cases we get excited because, for example, here factorization machines do seem to be yielding continuous additional improvement on the Amazon data set. We have to pay attention to exactly the magnitude of this improvement, so 0.05, and try to understand, well, is that really going to be important in our recommender system as it's operating online? Will that have a real impact on our users or not? So the point is that we get a saturation point, and we also have to ask ourselves, in cases where that point is not so clear, is the added improvement really helping us move forward? So another thing that comes up as you add more and more data is that for some algorithms, your computational complexity rises. So here we see the graphs of how the training time increases as the data set gets bigger, and we see that the picture that emerges is, well, using additional data costs us extra time and is maybe not worth it in the larger picture of things. Okay, so these are effects that are well known in the recommender systems community. Nobody is surprised at all by the research results here. We also performed some research results for ranking. So here's movie length 10 million Netflix. Again, the training set size increases. Here the metric is recall, so higher is better. And we do also see a flattening of the curve here. So basically, our conclusion is that there are several technical advantages of using the minimal necessary data in a recommender system. So summarizing, larger training set size increases storage and also increases the computational costs that you need. The evaluation metric improvement that you see when adding more and more data may not be significant or may not impact the user experience or the bottom line. That needs to be empirically verified. And finally, the key insight in temporal data is that stale data that is too old, may not actually improve the metric, and in a non-stationary data environment may actually hurt you. So these are basically the well-known technical advantages of not using more data than you need. And so given those advantages, it's a real question of, well, how did we get, as a recommender system community, so data greedy in the first place? Where does this data greed come from? Why does most RecSys research actually focus on maximal data, using as much as you can get your hands open? Are we horrible data greedy people? Well, the paper argues, well, not necessarily. Data greed is probably a historical habit created by offline testing. So think about it this way. If somebody hands you a standard data set and says, please test your algorithm on this data set for the purposes of reproducibility and cross-comparison of results, well, you need to use the entire data set, because you don't want the amount of data that you choose to use be impacting your outcome. So considerations of comparability and reproducibility does dictate data greed on offline static data sets. But that habit, as argued by this paper, seems to have spread over much of the research that we see in RecSys papers these days. And the main point of this talk here is that we need to turn back the clock and go back to days where we really analyzed how much data that the algorithm actually needed. So now I'm going to move forward with these advantages of minimal data, and I'm going to highlight some work that appeared at this year's RecSys that points to the benefits of actually thinking about which data you need and how much of it. So this is a paper by the group at the Hungarian Academy of Sciences. They had a great hands-on tutorial this year as well. Their paper is on online ranking prediction in non-stationary environments. Okay, so the data is changing rapidly. And they say that, well, we show that simpler algorithms can be updated online and therefore use the most recent data as well. And these often perform better than more complex algorithms that can only be updated periodically. And this is in contrast to the case where the testing is batch or the data is stationary. Okay, so they're also saying in this paper that the fact that we do batch testing, or testing on stationary data, this really impacts the way that people are using data. And here they really show the advantage of that last chronological data that comes before the recommendation moment. Okay, so that paper is interesting. So another one, also at the RecTemp workshop, at ACM RecSys 2017 was on the decaying utility of news recommendation models by the folks at TU Berlin, in particular Benny Killa. And so I'm not going through the graphs in detail, but what Benny is telling us is that replacing or updating models is necessary to maintain high predictive performance in news recommendation. And so here what we see is each of the colors represents a new model. And here he's looking at response rates, so the ability of the recommender to provide a response, and also the coverage. And we see that it goes cyclically. The fresh model then it gets worn out and needs to be replaced. So this is also another interesting paper that shows us that throwing all of your historical data into the model is not necessarily the best idea. Finally, another paper in the main conference now, and here they make the point that recommendations based on combined short-term and long-term interest results in increased accuracy, while recommendations based on combined short-term and medium-term interest yield higher news variety. Okay, so again, it's news recommendation, and focusing on the short-term, medium-term data instead of the whole historical data does not necessarily use the increased accuracy, but when you move to another metric, a metric that's also important in the online scenario, you do see a benefit. Okay, so those three papers from the other part of the conference, I think this is evidence that the community may be swinging back to understanding really what the value is of using historical data and not using it when it's not helping. Okay, now the question of, is all this data really necessary for making good recommendations? Well, that's not new for me. That question was actually already asked in 2013 by a short paper, which is called a Differential Data Analysis for Recommender Systems. And here, instead of looking at time truncation, they're looking at the value of data with respect to location. And without going into the graphs in detail, I can say that they show that different data has different value, and basically the paper states the case for differential data analysis, which is selecting data according to attribute values and observing the effect of the presence and absence of the data on recommendation accuracy. And differential data analysis, just like the data requirements analysis that we're advocating here, allows you to focus in on that kind of data which is actually helping you and discard the rest. Well, so here we come back to our technical advantages of minimal data. And so why would we want to discard the rest? Well, we have these technical advantages, but we also have the link up to responsible recommendation, which is our focus here. And this link up it occurs over privacy. Now, the easiest way of linking minimal data to privacy is via the so-called GDPR, the General Data Protection Regulation, which is going to come into effect in Europe in May of 2018. And one of the things that one has to do as a company that holds data of European users under this new regulation is respond to delete requests. Okay, if somebody would like their data deleted, you have to do it. So if you have a recommend system set up that actually doesn't retain data for some users or for some historical time, responding to delete requests is easier. So you can't delete something that you did not have in the first place. So that's the simple connection between minimal data and privacy and responsible recommendation. However, in this talk, I'd actually like to dive into privacy in more detail and show that this connection goes beyond just this legal consideration. And so we move to the second part, which is the question that I was asked at the banquet, well, why do you work on privacy? So unfortunately, I didn't, give this good answer at the time because I was sort of taken aback on the question about the question. So isn't it obvious why I work on privacy? But after reflecting a little bit, it boils down to the following. Algorithms and applications come and go, but the need for privacy is eternal. Okay, so privacy is something we know is important in the past, is important now, and will be important in any foreseeable future for RecSys. So with this motivation, let's talk a little bit more about what is privacy. Okay, looking at the O'Reilly book on privacy and big data, we see that there's several different definitions of privacy which are interesting to look at. Probably the most well understood is the physical and the organizational privacy. So physical privacy is the state of being free from intrusion into your personal space, including your possessions and your own body. And organizational privacy is secrecy, which is used by companies and governments to establish a competitive advantage and an advantage over enemies. But in recommender systems, we focus a lot on informational privacy, okay? And this is the state of control over information about you that is collected, stored, processed, or shared. Okay? And basically, the goal of protecting privacy is to keep the people about whom the data is, who generated the data, keep them in control of the data and the implications of that data. Okay, so information privacy, it's important to see this in terms of two actual types of information. So first of all is explicit information. Okay, we think most readily about personal information such as your date of birth, health records, things like that. Date of birth is maybe not so sensitive anymore. Health records clearly are, but there's also other explicit information. For example, this photo of Beyonce with her twins. So it's thundering a bit here in Chernobyl today, the day after RecSys. And basically, Beyonce went to great pains to make sure that this was actually the first photo of those babies that appeared publicly. So this photo not only illustrates explicit information that needs to be privacy protected, but it also shows the value that's placed on privacy. So we have celebrities and part of the reflex of their wealth and status is the fact that they value this kind of privacy and go to great ends to achieve it. And actually, in the case of Beyonce, are able to achieve it. That's explicit information. It's also important to protect implicit information. And this is information that is inferred via data. So you have interactions with an online system. You didn't explicitly post a picture of your children, didn't explicitly say anything about your health state, but inference algorithms allow us to discover this data. And one particularly dramatic illustration of this was in Australia, where Facebook actually showed advertisers that it could tell when teenagers were emotionally vulnerable. Okay, so basically, classifiers that are working on Facebook data are able to tell, when your sense of self-worth is at a lowest point, and this information must be protected. Now we trust that Facebook is, did an about face, so to say, and is protecting this information and not using it in bad ways. I mean, let's hope that we do this. But information about emotional vulnerability is there, even if nobody explicitly posts, "I am emotionally vulnerable at this moment." That must be protected under information privacy. Okay, so now, what does information privacy actually have to do with minimal data? So here's the bridge. Data, it's a mirror of who we are, but it is eternally an imperfect mirror. And because data does not reflect who we are, and it will never be able to do so perfectly, Okay, so we're stuck with data as being an imperfect mirror, and a lot of people who I talk to who are working in the field will acknowledge that data is imperfect mirror, but they'll see it as somehow fixable, or that we're converging to a point that data does reflect who we are. And it's really important to understand that that's not the case. Okay, so first of all, let's look at a couple of cases here. So case one, my sister binged on the Vampire Diaries using my Netflix account. So now my Netflix data reflects some kind of attraction to the Vampire Diaries, but actually this was my sister watching. So this is my data is a bad reflection of me, but this is a case in which it's correctable, or and there is work on how to tell the difference from who actually is watching, or divide down into sub-accounts, or do something to address this. Okay, so people are in agreement about that. And here's another case. So while I watched the Vampire Diaries and regretted it afterwards, again, my data reflects some kind of attraction to the Vampire Diaries, and it's more difficult to correct. So perhaps the algorithm or the system needs to ask me, or balance that off with other behavior. So here again, I could be convinced that, well, maybe ultimately we'll take care of that problem. But these two cases do not allow us then to assume that data will at some point develop to be a perfect reflection of who we are. Check out the third case. Thinking about the fact that my Netflix profile reflects that I have never watched the Vampire Diaries made me curious to watch it. Okay, so the paradoxical thing about data is that the existence of data and the interaction with data actually creates more data. So we're in an infinite regress there, and the mirror reflects itself, so to say. Okay, so let's say the paradox. The paradox is interaction with information creates new information. And because this is true, data is actually a maze of mirrors. Anytime that we collect data, interact with data, it creates more data. And data becomes the reality that it needs to reflect. So we're stuck with the point that data will never be a perfect mirror. We can't capture it. This woman is trying to take a photo of herself, and the fact that she's taking a photo is changing the image. Where is the actual woman standing? We don't know that. And doesn't make sense to ask that question. So because data is an imperfect reflection, it means that we, the people about whom data is, are left with a huge amount of work. And that work is created by the fact that data, in its imperfections, poses actually questions about us that it itself cannot answer. For example, why were you watching Vampire Diaries last Tuesday during your shift? So that's a question that's posed by my Netflix data, which that Netflix data can't answer. I have to answer that question. Okay, well, actually, it's my sister that was watching. And this is answering all these questions is work. Okay, we need to perform work in order to correct the picture of us that the data projects. Okay, and this is why we need privacy, because if you can imagine answering every single one of those questions posed by data, I mean, this would take us all day. This is really, data becomes this thing that basically, attacks us. And in fact, this very sort of dangerous side of data was very well described by this article in The Guardian, nearly 10 years ago now. Personal data is as hot as nuclear waste. And here, Cory Doctorow argues that we should treat personal electronic data with the same care and respect as weapons-grade plutonium. It is dangerous, long-lasting, and once it's leaked, there's no getting it back. Okay, so we're we're playing with fire when we're playing with data. Incidentally, here when I went to make the screenshot, then we have a little advertisement, which is of course placed there by some kind of recommendation, and well, they're recommending that I look at IEEE Explore. So basically, my browser is saving all of my data, and the best it can do is tell me to look at IEEE Explore, which is something that I do daily anyway. So it's a wonderful case that I didn't even plan of a system that's collecting my data like crazy, basically to do something that is perfectly useless. Except it now provided a good example for this particular talk, but that was sort of an interesting aside. So we see extra data used to improve a recommendation, which does not have an impact on the bottom line, which I talked about in the first part of this talk. Okay, so this picture, I just went on the, Google image search and pulled down a couple of the classic pictures of information overload. Okay, so this is a classic picture of information overload. And in fact, the whole field of recommender systems identifies with, the task of actually protecting a user from this wave of information overload. And now if we see data and its imperfections causing questions that the user needs to respond to, needs to correct, the picture of information overload is more like this, okay? So we're bombarded here, it's being bombarded with emails, but we're being bombarded with these questions that require our response, okay? And basically, this leads to information exhaustion. And so the reason that we need privacy, in addition to preventing direct harm and preventing this feeling of this feeling of creepiness when our privacy gets violated, is that we need it to have basically a little umbrella around ourselves. So some questions can get through. That's fine. Just like a recommender system, sorts out that wave of data and gives us recommendations, and people can ask questions about us. It's not a problem. But we need to prevent the information exhaustion that is caused by constantly having to make corrections in data, which can never, as we've shown, inherently perfectly reflect who we are. So that's the connection between data and privacy, and what it does to people. Why we need to look at privacy, and why why minimal necessary data should help. So our understanding of responsible recommendation, the topic of the workshop, is as follows. Responsible recommendation is recommendation that serves the people whose data it uses, okay? So as I said, no creepiness, no harm, and no information exhaustion. And one of the ways that we can prevent this information exhaustion is just to simply get rid of data that we don't need, data that could create questions that really we don't have to answer. And that forms that productive umbrella over our user, to shield them, over ourselves, to shield us from, this onslaught of ways in which we have to say, no, I'm different than my interaction data. I'm this, I'm that. It happened because of this, it happened because of that. Okay, so this leads us to the principle of minimal necessary data, which is stated as follows. If two recommender algorithms achieve the same effectiveness, the better algorithm is the one that requires less user data. And our point that we're making with this paper, the thing that we're arguing for, that we're advocating, that in order to demonstrate compliance with the principle of necessary data, papers should carry out training data requirements analysis. Now, the good news here is that actually we used to do this. Here's a highly cited paper from 1998, Empirical Analysis of Predictive Algorithms for Collaborative Filtering. And this paper includes a learning curve. So training set size, and here's a rank score, so higher is better. And the paper shows that, well, we get saturation after about 10,000 interactions here, and here we don't see any additional improvement. Okay, so the authors of this paper actually checked to see how much data they needed. Well, their conclusion is like 30,000 is enough, and not what I'm saying here is that, if you see this kind of a curve, that you should actually, stop yourself at 10,000 there. But the point is this: plotting these learning curves is common practice in machine learning. Apparently used to be done in recommender systems, but we sort of got out of the habit. We just got out of the habit, and we got into the habit of data greed. So this paper, I hope, will convince people that they should look to see how much data is really necessary. Reducing data reduces information exhaustion, and in addition to the other benefits of privacy. Information exhaustion is, of course, the thing that drives us as a recommender system community, and the privacy is just another aspect of handling information overload, is the point there. Responsibility requires relatively small changes in current practices. Just going back to doing this requirements analysis, this learning curve graph, takes one section in your paper. That's it. And finally, we point out, well, hey, over the years, we're getting pretty good at doing cold start. If we use minimal necessary data, we can actually leverage what we've learned about cold start over the years. And so it's minimal necessary data is just a really cool new recommender system challenge. And I close with call. Let's be brave. We've been here before. We've looked at our data requirements before, and really it's time that we start doing that again. It's the responsible thing to do.